Welcome to another session of differential geometry class. Today we are going to deal about some examples of geodesics. Last class we have seen what is a geodesic. So let us recollect what is a geodesic. A geodesic first of all is a parameterized curve alpha from I to S. So a geodesic means first of all it's a parameterized curve alpha from I to S where acceleration is everywhere orthogonal to S. So what you're getting is alpha double dot of t is belongs to S of alpha of t perp. So this is our key idea. Now to show that something is going to be a geodesic, what we have to show is that its acceleration is belongs to S of alpha of t perp. That means, in another way, we know that the normal space is spanned by del f of p, right? Or we can say that the n, right? Then what we have to show is that if something is going to be a geodesic means we want to show that this acceleration alpha of t is some multiple of our n, that is the normal component. Suppose we can show this means it shows that alpha double dot of t is perpendicular to or orthogonal to S of alpha of t perp. So our idea is to show that acceleration is a multiple of normal. So here is the first example. For each a, b, c, d belongs to R, define alpha from I to R3. So alpha is defined from I to R3. It's in the three-dimensional space by alpha of t equal to cos at plus b, comma sin at plus b, comma ct plus d. Okay, so like this we have defined your alpha. Now we want to show that this alpha double dot of t, that's the acceleration, is a multiple of normal. So first of all we can split this into its components. So we are writing this as this equal to you can write actually alpha 1. So I am using the notation x1 of t, x2 of t, comma x3 of t notation. Now this implies that x1 means this, x2 means this, and x3 means this. So we have mentioned everything in terms of components. Now what we are getting is when you are multiplying this square of x1 square plus x2 square, you will get it as 1, right? This alpha of t on the cylinder x1 square plus x2 square equal to 1 in R3. So this is a geodesic. So what is this? This curve is nothing but parametric equation of cylinder it is. So we want to show that cylinder is a geodesic. So we want to find what is alpha dot of t. Alpha dot of t is cos is there, so minus sin at plus b into a, right? So minus a. Next sin bt plus d, you will get cos at plus b into a, and last term c, right? Now what is alpha double dot of t? Alpha double dot of t, alpha dot of t, of course, is defined as alpha of t comma. We should write like that. So alpha double dot of t is again alpha of t comma double dot, right? So it will become minus a square cos at plus b, comma minus again cos is there, a square sin at plus b. and 0. So our alpha dot of t is alpha of t comma minus a square cos at plus b minus a square sin at plus b comma 0. Now alpha of t is the cylinder, as we have said. Thus the cylinder is given by S equal to F inverse of 1. Right? So cylinder is given by S equal to F inverse of 1. So we can calculate what is del F of x1, x2, x3. See, what for we need this one? Because we know that normal is defined by del F of, or normal is spanned by, or normal space is spanned by del F of P. So that's why we are finding this. So del F of P is equal to is again x1, x2, x3, comma, it will reduces as 2x1, 2x2, 0. 2x1, 2x2, 0. Now, what should be? Because f is going to be this. x1 square plus x2 square. So here f is defined as f of x1, x2, x3 equal to x1 square plus x2 square. So the last component 0. Now we want to find what is del f of x1, x2, x3. So del f of x1, x2, x3 is equal to square root of, you can get square root of this square plus this square. That is 2x1 square plus 2x2 square. So that will result root 4, that is 2. So norm of del f of p we have found out. Now what is normal? Normal is defined as n of p is equal to del plus or minus del f of p by norm of del f of p. Now we are having these two things. So you can easily calculate what is your normal one. So this one. So n of x1, x2, x3 equal to plus or minus 1 by 2 into x1, x2, x3, 2x1, 2x2, 0. So we have calculated your normal. Okay. Now if this is the normal, then we have already calculated and kept what is the x ratio. So x ratio is minus a square cos at plus b minus a square sin at plus b. Can you combine these two, or can you connect these two? Will it be a multiple? What is x1? x1 means cos at plus b sin at plus b. So what we are getting is x ratio is equal to plus or minus a square into n of alpha of t. Just you compare this and this, you will get plus or minus a square into n of alpha of t. That means your x ratio belongs to the normal space. That means alpha is a geodesic. So let us have some, if you are putting some value for a, b and c, you will get this curve like this. The first one, alpha of t is equal to cos at plus b sin at plus b ct plus d. In the cylinder, x1 square plus x2 square equal to 1 when a equal to 0. When a equal to 0 means it will become cos b sin b and ct plus d. In this case, cos b sin b is the squaring and adding, you will get 1 itself. So it is the unit circle. Now ct plus d represent the straight line, right? So what you are getting is all the circles arranged in the x3 axis. Unit circles arranged in the x3 axis. So that is nothing but the cylinder, right? Now for b, the b1, c equal to 0. C equal to 0 means this again will represent the circles, and c equal to 0 means you will get only d value over here. So that will result again circles, right? So the next one, when you are having a not equal to 0, and C not equal to 0 means you will get the spirals like this. Like this spirals. That means going like this. Then like this. Along the what you're getting is along the cylinder. So case 1, A equal to 0. We have discussed it here. When A equal to 0, then alpha of t will become like this. For B belongs to R, it's you will get x1 square plus x2 square equal to 1. So the geodesic alpha is a straight line here. Right? How are you finding? A equal to 0 means what you are getting is cos B plus sin B comma ct plus d. For B belongs to R, cos B sin B will be the is a point on the circle. Right? Now you are taking a circle and a point over the circle, that is your point is cos B sin B when you are fixing B. Now what you are going to do is you are going changing your x3 direction. So x3 direction means in this direction. So you are getting is a straight line. Right. Now case 2, C equal to 0. In this case, the geodesic alpha is a circular ring around the cylinder. Because whenever C equal to 0 means you are getting only D. So your x3 is fixed. Right? So whenever your x3 is fixed, you want to consider a circle along this one. So this is a x3 axis. Now this is the point D. So at D what you are getting is a circle. And case 3, in this case the geodesic is a spiral or a helix. Now we are having the second example. Let E1, E2 be a pair of orthogonal unit vectors. So what is the meaning of that? E1 dot E2 equal to 0. So orthogonal unit vectors for the norm of E1 equal to norm of E2 is equal to 1. Okay. Unit vectors in R3. For each A belongs to R, we want to define alpha of t equal to cos AT E1 plus sin AT E2. Then norm of alpha t square. What you will get? It should be cos square AT plus sin square AT, that's equal to 1. Thus, alpha is a great circle or a point if A equal to 0 in R3. Thus, alpha is a geodesic in a two-sphere. This entire problem can be asked like this. Show that the great circle is a geodesic. What do you mean by great circle? Great circle means when you're having a sphere, you take its section like this. So whenever you are getting a bigger circle here around the cross section, so if I am cutting over here means I will get a circle like this. If I am cutting over here, I will get a circle like this. Now we go for those circle which is having largest radius. See, evidently the largest radius means it should pass through, see this one, along the center it should be the diameter, right? So we will say that this is the great circle. So we want to show that the great circle is a geodesic. So again what you are going to do is, you want to show that the acceleration is a multiple of normal. So first you are finding what is alpha of t and what is alpha double dot of t. alpha dot of t means alpha of t comma, what is your curve equation? Alpha, see this one, cos at e1 plus sin at e2. So that will be minus sin at e1 plus a cos at e2. So you are finding again alpha double dot of t. Alpha double dot of t is equal to, again it is at alpha of t comma minus a square cos at e1 minus a square sin at e2. That's equal to, a square is common, so I am taking minus a square outside. So minus a square into alpha of t cos at e1 plus sin at e2. Also, we want to have your normal, so we want to find what is the function f. So f of x1, x2, x3 is given as sphere, right? So x1 square plus x2 square plus x3 square. Now we are finding what is del f of x1, x2, x3. That is 2x1, 2x2, 2x3. So this is your del f of. Next we find what is norm of del f of x1, x2, x3. That is 4x1 square plus 4x2 square plus 4x3 square, all thing raised to 1 by 2. So it will again result 2 into x1 square plus x2 square plus x3 square, all thing raised to 1 by 2. So what is this quantity? 1 unit sphere, right? So this entire norm is going to be 2. Now we are finding what is normal component. That is n of alpha of t means del f of alpha of t by norm of del f of alpha of t. So that will reduces as plus or minus 1 by 2 into x1, x2, x3, 2x1, 2x2, 2x3. Now we want to have, can we combine these two or not? Okay, so what you're getting is, this means minus a square into alpha of t cos at e1 sin at e2. So this can be written as alpha of t comma cos at e1 plus sin at e2, right? Since you are getting this to be as 1 by 2 into 2 is common, take 2 outside, you will get 2 by 2, that's 1. So remaining is x1, x2, x3. So I will write it here. What you are getting is x1, x2, x3. Oh, sorry. We are getting from here. Here we are going. So plus or minus 1 by 2 into x1, x2, x3, 2x1, 2x2, 2x3. So when you collecting the common term, you will get plus or minus 1 by 2 into 2 into x1, x2, x3, again x1, x2, x3. That means this is nothing but plus or minus, first term is x1, x2, x3, again is coming x1, x2, x3. So that is alpha of t comma alpha of t, right? Now what is alpha of t? Plus or minus alpha of t comma alpha of t is nothing but cos at into e1 plus sin at into e2. So can you combine now these two? When you combine these two, what you are getting is alpha double dot is equal to, alpha double dot is like this. So this one is same, this component is same, only thing is that 1 minus a square is an extra term. So you can write this as plus or minus a square into n of alpha of t for every t belongs to R. So this implies that your alpha, that is the great circle, is a geodesic on the 2 sphere. So alpha is a geodesic on the 2 sphere. So we have proved that great circle is a geodesic. So hope you understood how to prove a given curve is a geodesic or not. So what we have to do? We want to express the acceleration as a multiple of the normal. So let me wind up the session here. So we can have more examples in the next class. Okay. So thank you for your patient listening. Thank you.